Thank you for coming, and thank you for inviting me, Impetus team. Thank you. Let me start with my talk, which is essentially on blockchain scalability and secure smartphones. Before I kind of motivate why we should do and when we should study these problems, let me take you through this first obvious question, which is how many of you here have actually used a blockchain-based application, including payments, for instance? Almost everyone. That's pretty cool. So now that you have used it, you must have seen this one, which is, we have been talking about games and, ways to advertise. This is one very interesting and very cute little application called CryptoKitties, where the idea was that you digitize cats, and then you could take two cats, so you can buy cats, you could sell them, and then you could actually breed them and have new cats, and you could sell them again. Now, don't ask me why and since when cats have started laying eggs. But apparently, in the crypto world, anything can happen. So this app became very, very popular to an extent that it kind of became the most popular app on Ethereum's blockchain for a certain while. So to an extent where this cat was sold for over $100,000. So you can imagine how crazy people were to actually buy those cats to play that game. Yeah, but does it deserve $100,000? Maybe not.
You got better stickers.
Yeah.
Stickers get better than that.
Yeah. So sorry.
When you get served on Zilliqa, you have to pay.
So the point here is that these cats are, people started really using that app, and to an extent where people were willing to pay such a big amount of money for this simple digital cat. Yeah. So it clearly shows that certain applications can actually be built on blockchain, and they can become really popular. So there's this utility of blockchain. It actually shows that there's some utility for blockchain for real world applications. But the problem is the following: when this app became really popular, what happened was that the underlying blockchain platform, which was Ethereum in this case, was not able to support that application. There were so many users who were trying to play this game, and the underlying blockchain platform was just not able to cope with that traffic, to an extent where, around December last year, the gas price went so high that you can see a spike, and it's coming from CryptoKitties. And you can see the numbers, like it increased by over 4,000%, by around 4,000%. So it clearly shows that whenever you build a blockchain application, and if the underlying platform is not able to support that traffic, you will end up with those kind of issues. And of course, CryptoKitties, faced the same problem that we expected. And so they had solutions. One obvious solution was that prevent users from playing that game. So what they did was they doubled the price of breeding cats. And once you do that, you are actually kind of forcing users to kind of push away from this application. Now imagine you as an app developer who wants to build a very popular app, and the moment it becomes very popular, you want to push your users away. So this is a very, very sad incident. So they did that, but of course they realized that there's not a solution to fix this problem, and the ultimate solution would be something that actually, that would be more long term, and that would actually solve the underlying scalability problem of underlying blockchain. So there's a clear need of building a scalable blockchain platform that can actually support real world applications such as CryptoKitties. So to put things into perspective, here are the popular blockchain platforms and the throughput that they give. So the throughput that they yield. So the number of transactions that they process per second. So Bitcoin and Ethereum, they are roughly around 10 transactions per second, while a simple payment application, which is Visa, which is a real world application, it processes around 5,000 to 8,000 transactions per second on average. And it can actually go pretty high in peak hours or in Christmas time, for instance. So again, there's a clear gap between what blockchains or existing blockchains or popular blockchains provide in terms of throughput and what a simple application that will be implemented in the real world would require. So obviously, the entire community, if you are involved with Bitcoin and Ethereum, the entire community realizes that there's a problem, and all of them have solutions to fix this. So I'll just go through a few of those solutions and some of the limitations and what they can give. So the first, most obvious solution is to increase. Oh, sorry, it was not supposed to come right now, but anyway. So the most obvious solution is to increase block size. So if you know how Bitcoin and blockchains work, so blockchain is a chain of blocks, and a block can contain a bunch of transactions. So if you increase the size of your block, you can fit in more transactions, and hence you can have high throughput. Now, of course, so once you, let's say, increase your block size from, let's say, 1 megabyte to 2 megabyte, you can fit more transactions and you can double throughput. You can keep doing it, but the problem is that you have to stop somewhere because of network and constraints and limitations. So if you from a layman's perspective, let's say you have a simple bus which has a capacity of 40 passengers. If you want to double the capacity of this bus, you could convert this bus into a double-decker bus, and you could have let's say double the capacity now. But you cannot keep on doing this, because then you would end up in a bus like this, where if people like me or you have fear of heights, you won't want to ride on this bus. And again, then you have security issues as well, because certain cities and certain countries have height limitations. So certain buses like these, they cannot actually go through. So this solution gives you very immediate throughput results. So you just you change one parameter, and then you can have very high throughput. But they have their own limitations. You have solutions like what are called off-chain solutions, where the idea is that reduce the traffic that goes to the main chain or the main network. For instance, here, let's say I have a very fancy Tesla car, and I of course it's an electric car, and I go to this charging station every morning to charge my car, and I pay, let's say first day I paid $5, second day I paid $2.25, and so on and so forth. Now, instead of sending all these small little transactions to the main network, I could be clever. And the idea is that what you could do is you could kind of assign a contract between you and the charging station, and you could say, look what, I'm not going to pay you every day, I'm going to pay you, let's say, every month. So you sign this contract, and you send this contract, let's say, to the main network, and then you would send off-chain transactions. Will kind of reclaim entire money in one go. So you have reduced all these small little transactions to just 2 transactions, the start and the end, and then the rest are all off-chain. So you're definitely reducing the number of transactions that goes to the main network, so you'll get high throughput. But then you are losing in terms of different properties that come through blockchain, right? You first have to ensure that you're losing in terms of transparency and let's say decentralization, of course, because you need to probably build another network on top of regular network, and that again has its own issues. The other question is, can you actually extend it beyond payments? People are actually looking into this problem, and we have a solution for that. But again, this solution has its problems again, and that's why we decided to work on something different, and which is sharding. So let me take you through this idea of sharding and how it works at a very higher level. I'm not going to go into deep technical details. We can discuss after the talk. So first, what exactly we are doing with sharding? So the idea is that when your network grows, your throughput should grow as well. So these are actual numbers that we observed from our internal testnet. So when we started with, let's say, 1800 nodes, we observed a throughput of around 1200 transactions per second. And when we doubled the network size from 1800 to 3600, we observed that the transaction throughput doubled as well, from 1200 to 2488 transactions per second. So this is pretty counterintuitive, because if you look at how Bitcoin and Ethereum work, the moment you add more nodes, things become slower and slower. And here is slightly different. It keeps on growing. Now, so where is this idea coming from? And the idea is as I said, this is the idea of sharding. And it comes from, if you're familiar with databases, sharding is pretty known in that field, where what you do is you have a big table. And what you could do is you divide that big table into smaller number of rows. So let's say you could take the first 2 rows, and one server would only handle requests coming to that 2 rows. So that's an idea that's very, very prevalent in database systems. But it was not known whether you could actually apply the same idea in the context of blockchains. So some of our team members wrote this academic paper in 2015, where we showed that you could actually have the same idea and implement that in the context of blockchain to solve the scalability problem. So what we did at Zilliqa was to implement this idea into a real-world deployment and then test it. So first, we implemented it in a permission setting where where you had a set of nodes that were predefined. These nodes were essentially banks and exchanges, and we tried this with these banks and exchanges in Singapore. We felt that okay, it works pretty well, but the problem is that in a permission setting, you don't have too many nodes. And if you don't have nodes, you cannot scale up, because the whole idea of sharding is that if you have more nodes, then only you can scale up. And in a permission setting, you just don't have that liberty. So how do you actually leverage and exploit the idea of sharding? The only way to do is to make it public, because when you make your chain public, you can invite nodes from the community to join, and then you can have a lot of nodes, and then you can have scalability. So this is exactly what we did. And this is how Zilliqa came into existence, where we built this idea of sharding and implemented it in a open public setting. So I'm going to this, at a higher level, if you have a scalable blockchain platform, then you would also reduce the cost of processing transaction, right? Because if you look at Bitcoin and Ethereum, right now you have to compete for the 5 to 10 transactions that goes in a block. Instead, if compared to that, now you won't have to do that because you have a higher capacity to process transactions. So now let's imagine you have a blockchain platform like Zilliqa, which processes a lot of transactions per second, which has a very high throughput. What kind of application you can build on top of that? Since we have been talking about digital advertising, we can't ignore that fact. So we can actually build a digital advertising supply chain on Zilliqa. I'm not going to go into the details of it because we have been talking about this since the start. So they have their own problems, and this market is pretty big. You have big giants like Google and Facebook involved in this market, and you have things like ad fraud, people using ad blockers, and try to destabilize ad-based economy in some way. So you need a way to make it more transparent to ensure that those middlemen that are not necessary could be removed from the system. And so we felt that this is a very important application that you can think of to build on a blockchain. The other reason is that it involves a lot of players, because on the one hand you have advertisers. You could imagine all advertisers like Adidas, Nike, who want to advertise their product. On the other hand of the spectrum, you have the publishers like BBC.com, Wall Street Journal, which publish those ads. And then at the end, you have users who actually see those ads. So it covers a wide area, or wide group of entities in this application. But obviously, imagine building such an application on existing platforms. You won't be able to do that because Google alone, delivers around 1 billion transactions per day. And if you look at Ethereum, they process around 1 million transactions per day. So there's a huge gap between what existing platforms offer and what you require from such an application. So even if, let's say, Ethereum decides to dedicate the entire infrastructure to process only ad-related transactions, even then, this application cannot be built. So what we are trying to do is we have partnered with a company called Mindshare, which is a digital media advertising agency, and to understand what are the problems that they face and how we can solve them. So we are planning to build a part of ad supply chain on Zilliqa together with Mindshare. Of course, digital advertising is not the only application that you can think of. You could imagine questions like, can you build an application like Uber on blockchain? Or even simpler, can you imagine building a regular payment network on blockchain? Which is not the case yet. So all these applications actually require very high throughput, and if you don't solve the scalability problem, then you won't be able to build those applications that will require a really scalable platform. Okay, so now let me take you through a very quick overview of how Zilliqa works and how sharding works. So the higher level idea is that if you know how Bitcoin and Ethereum work, when you as a user creates a transaction, you send it to the network, and every single node in the network processes and validates your transaction. So it's very decentralized, it's very secure, because even if a few nodes are down, the system will continue to process your transactions. But then it's very redundant as well. Because imagine your single transaction being processed by a network of 40,000 nodes. So we felt that you could do better, and that's why we do this, implement this idea of sharding. And what happens in sharding is that you could start with a very large network, let's say a network of 10,000 nodes, and then you could divide them into smaller groups, let's say each group containing 1,000 nodes, so that when you have some transactions, a lot of transactions, you could divide those transactions into separate parts, so that a shard, this smaller group processes only a subset of all transactions, not the entire set of transactions. And then if you can do that, then you could process transactions in parallel, and hence you can have high throughput. So high level idea is that you take your network, you divide it, and then you try to conquer it in parallel. Of course, the idea is pretty simple because you're just trying to divide and trying to run things in parallel. But at the base layer, things are pretty complicated. One is how do you actually build those shards? What is the number of nodes that you want to put in the shard? If it's large enough, how do you ensure that the consensus that you run in each shard is very efficient? So what we're trying to do is to take an old school consensus protocol called PBFT, and we use this consensus algorithm within each shard. But in order to make it more efficient, we use some clever cryptographic primitives to make it more optimized and efficient. So okay, so there's a very quick overview of Zilliqa and sharding. Now let me take you to do smart contract, because I said that we're going to talk about scalability and secure smart contracts. So we are also working on smart contracts as well, because we feel that there's some this line of problem. So let me tell you what exactly is the problem with smart contracts. So for those who have who have interacted with Ethereum's blockchain, you must have heard of DAO. So where an attacker was able to find a bug in a contract and was able to steal funds from that contract to an extent where around $60 million were stolen. And the impact was that this contract this bug forced the Ethereum network to actually forge, and hence you have Ethereum and Ethereum Classic right now. Then again, of course, that was not an isolated incident. Very recently, a month or probably 2 months ago, you had this incident from Parity where someone who was playing around with the smart contract was able to destroy the contract, and around $300 million were frozen in that contract. So you could see that there's money there, but you just can't take it out. So, of course, these are not going to be the only incidents. The next one is probably, just outside the door, and you might, see it probably tomorrow or the after tomorrow. So there's a definite problem. There's a problem with smart contracts, so the way the smart contracts are being deployed and how safe these contracts are. But let me take you let me try to explain to you why these contracts are actually buggy to some extent, or why these contracts are not very safe. So the first, the major problem is its complexity. So smart contracts are generally like any program that you want to write. So they can do a bunch of mathematical computations like additions, multiplications. They also manipulate a global state. So imagine you are involved in an ERC20 or ICO contract. This contract would maintain a mapping between which user contributed how much amount of money. So this state is being maintained by this contract. And then a contract can actually talk to other contract as well. Now imagine these are very nice features to have, because then you have a lot of flexibility in building the contracts that you want. And you can build very interesting real world applications. But then you have issues. The problem is that when you have such a contract, you have to consider the fact that you're running it in a very Byzantine and very malicious environment, where you as a user might be clever or stupid, and you might try to interact with this smart contract in a very stupid way and try to steal money from that contract, or try to freeze money in that contract. Or you could be your miners who are sitting in the network, they could themselves be malicious and try to do funny stuff. Or the worst part is that a contract, when it talks to another contract, that contract can still be malicious. And this is what happened in the case of DAO. So now imagine all of these nice features happening with smart contracts, and all of this is actually being run in a very malicious and Byzantine environment. And this creates a lot of risks. So when you are a user, when you're a developer, when you develop a smart contract, for you it's very hard to say that my contract is very safe, because you don't know. When you deploy the contract on the network, You don't know what's going to happen with your network because of all these complications. And furthermore, so for you in general as a developer, for you it's very easy to say that my contract is going to behave in a certain manner, in the sense that it's going to do this, this, and this. But it's very hard for you to say that my contract is not going to behave in a certain manner. So in more concrete terms, for a contract like these, it's hard to give very formal guarantees about the contracts. For instance, you can't say, it's very hard for you to say that my contract, I can guarantee with mathematical guarantees that my contract is going to just do this, nothing beyond that. So there's lack of formal arguments around smart contracts. And one reason is that because of all these complexities. And of course, when you have a problem, you want to solve them. And this is where we try to do as well. So we felt that, of course, smart contracts need some kind of, needs a little bit of work. And we decided to build a new smart contract language that we call Zilliqa. And the idea is that, at a higher level, the idea is that you take Solidity and you try to simplify it and structure it in a way that it becomes slightly easier for developers to make or write safer smart contracts. So essentially, Zilliqa is based on what is called an automata, where so this is essentially a light bulb represented as an automata, where a light bulb will have a bunch of states. So this light bulb will have 3 states: off, dim, and bright. And then a user can interact with this light bulb and can change the state of the system. So a user could press once and then the light bulb will go from off to dim. If it presses for a longer period of time, then it will go from dim to bright. So the entire contract can actually be defined using, let's say, a previous state of the system, an input coming from the user, and the next state of the system that will be decided by the contract. So it gives you a very proper structure to how a contract will look like, or how a contract will behave. There are multiple things that have been done with the smart contract language that makes it pretty safe. So here's what fragment of a contract in Zilliqa would look like. So here's a contract, a Kickstarter contract. So for those who are not familiar with Kickstarter, the idea is that, let's say you have to build an app, but you don't have money to fund your project. What you could do is you could ask the crowd to fund your project, and you could ask them to give money to your project. And then if you have enough money, then you could start, building your project. So this contract has, let's say, 3 parameters that will get initialized when the contract gets created, just as in Solidity. So you have an owner who actually receives the fund at the end. You have a deadline before which every crowd member has to submit or send money. And you have a goal, which is, let's say, I want to raise $1 million. And if I'm not able to raise $1 million before this deadline, I'm going to abandon the project. And I'm going to refund all the money that I've received. And of course, you need to maintain a mapping between which user contributed how much amount of money, and you have a simple Boolean flag that says, okay, whether the campaign has been successful or not. And the interface gives you 2 functions right now. One is donate, so any user can call this function and donate money to this contract. And then if the campaign has failed, then you could call the other function reclaim and try to take back your money. So generally speaking, it's very similar to how you would write a contract in Solidity. Okay, I'm not going to go into the details of it, but the high-level idea is that if you structure your language properly, you could eliminate incidents like that at the very language level. Okay, you can ignore this slide. But the problem is that you could eliminate certain bugs, such as the bug that happened in DAO. But can you guarantee that you haven't missed other bugs? And for that, you need formal verification, formal proofs. So what we did was as an example, we took this Kickstarter contract that I showed you in Zilliqa, and we modeled it in a theorem prover that's called Coq. And we could show 3 very interesting properties about the contract. So we could show that the contract will always have enough funds to refund people if ever it refunds. So it's not going to leak money as happened in DAO. So it's not going to lose money. The contract will never manipulate the contract records. So if, let's say, you have contributed $5, I'm not going to change it to $10, or I'm not going to reduce it to $2. So the contract will maintain the correct contribution records. And eventually, if ever the contract has to refund money, it will refund the right amount of money. So this gives you very strong guarantees about how the contract will behave. And if you try to introduce bugs in the contract, the proof will break. The proof would say that no, your contract is no longer safe. So there are a bunch of, the work has not ended. We are still working on it. There are a bunch of things that we are working on. For instance, we don't want developers to learn a new language because nobody wants to learn a new language. It's pretty hard. So we are working on, we believe that Zilliqa won't be a language that people will be directly coding in, even if it's you can code. We are working on a higher level language that will have syntax similar to Solidity. So if you're familiar with Solidity, you can use very similar syntactic, constructions to write a contract. And then we will have compilers that will take that contract written in a higher level language and compile it down to Zilliqa. There are a bunch of other things that we are working on. I'll be happy to talk about them after the talk. So where are we now? We have, as I said, we observed throughput of around 2,500 transactions per second back in December with a network of 3,600 nodes. We have a testnet which is live. So this testnet has, to some extent, it's very limited in the sense that you could send transactions, but you cannot run a node in the network right now. But we have an explorer and a wallet that you can use in combination to interact with that network. Of course, we are constantly improving the code and adding new features to it. We have a smart contract paper that was published in January this year. We are working on a smart contract implementation right now. We will be demonstrating the smart contract interpreter in 3 days' time, I guess, when we are back in Singapore.